So we saw the properties of signals now, and then we also saw properties of signals, different kinds of standard signals, and how to manipulate signals. We'll end the discussion of signals with one important kind of signal. Okay, this signal is what we call as Dirac delta function. So this signal was in fact first invented by the physicist Paul Dirac, and hence the name Dirac. And it's a delta function in the sense that it represents a small change in the signal's value, and hence the term delta. Okay, so the signal is represented by a small arrow. Okay, this is the representation, graphical representation of the signal. Okay, so where is this Dirac delta useful at all? So Dirac delta becomes very useful to model instantaneous jumps in our signal's value. So remember, the entire signals and systems course is where we are trying to model real life data or real life signals using mathematical models. So you have current and voltage signals, you want to represent them. So use a function to represent it. Those signals are represented using a model. Then you have a system, then you try to model them, that we'll see later how to do. So essentially this is a mathematical model. So how do you mathematically model a sudden jump in voltage or sudden jump in current? So in fact this happens. Remember, the current across a capacitor, we said that is modeled by some dV by dt. So in a circuit, let's say you have a circuit like this, and then you just close a switch. So whenever you close the switch here, then the voltage is applied across this resistor or across this capacitor. So now let's say your voltage is of the form of a step function. Okay, so when you close the switch, there is a non-zero voltage. Till that point, there is a zero voltage. Now what happens to the current? Right? So current now becomes basically nothing but the derivative of the step function. Now what is the derivative of the step function? So in this portion of time, it is 0 because the time, negative values of time, has a constant value of voltage which is 0. So slope is 0, so you have 0. And in this portion also there is a constant value of the voltage. It's a straight line, but the value is 1, but the slope is 0, so it is 0. So what happens at t is equal to 0? At t is equal to 0, the slope of this curve, which is a step function, is infinitely large, because within a very small time, it attains value 1 from 0. So if you compute the slope here, it's basically infinite. Then our derivative of the step function should look something like this, where at t equal to 0, it has to attain a value which is infinite. Okay, and whatever before that it is 0, whatever after that also it is 0. So at just one point it attains a value which is infinite. It's sort of modeling the jump in the current which is instantaneous. So suddenly, instantaneously, it gives you a spike. So this is what we see often, right? There is a lot of spikes in voltages and currents that we encounter in real life. Why is that? Because there is a sudden change in the voltage or current across the circuit, which results in a spike in the current or voltage, depending upon what is the reactive component that is present. So these spikes are modeled by Dirac delta function. So we'll say that the derivative of the step function is given by this Dirac delta function. And how does this look like? The Dirac delta function, we'll say that is in fact equal to 0 for t not equal to 0, but at t is equal to 0, we'll say that it is almost infinity. So this is how we'll define the Dirac delta function, but there is more to this function. So it is not just a function which simply attains infinite, but the interesting part is when you take the integral of the Dirac delta function, we'll say that it is equal to 1. So why is this function like this? So technically it is not a real function. It is just a mathematical model to represent spikes, right? So if we have infinite, then it can mean that the amount of area that is present under this curve could be infinite, or or what is happening to this spike in real life. How does this model the spike in real life? It's not like we get infinite energy suddenly, right? So everything is finite. So for this reason, we have to ensure that the model reflects reality, and that model is such that the area is 1. So what does this actually mean? So what we are saying here is that, okay, I'm trying to compute the slope. The slope at t is equal to 0 is such that it is almost a sudden increase, okay? It's almost like a rectangular function, and the width of this rectangular function is epsilon, and the height is, let's say, 1 by epsilon. So what is the total area? The total area of this is 1, no matter what the value of epsilon, for all values of epsilon, okay? But I can make this epsilon arbitrarily small, meaning this epsilon can be like 10 power minus 200, which means the magnitude or the amplitude of this function will go really, really large. So that is what we are saying. In an infinitesimally small time, that is epsilon, the amplitude is infinitely large, that is 1 by epsilon. So if you compute the slope of the step function, in real life, the slope will not increase instantaneously, it will increase in a very short time. So it's almost like, so this is what you will see in real life, right? So the slope will increase from 0 to 1 in a nice smooth manner in real life, but the time taken by the real life systems to go from 0 to 1 is really, really small. Like, of course, we know that, all the electrons travel almost like with the speed of light, or the electric field travels with the speed of light. So almost with the speed of light, it goes from 0 to 1, which means the time taken here, epsilon, is really, really small. So as you can see here, then the time taken is so small that in this duration, when you compute the slope, it's almost like 1 by epsilon, and the duration for which the slope is non-zero is epsilon, right? So the derivative in this region turns out exactly to be this rectangular function, because here it's like a straight line, okay? Straight line's slope is just a constant, and that constant is 1 by epsilon. So this is what we get when we take the derivative. Fine. Now this epsilon is so small, we say that it is almost equal to 0. And because it is almost equal to 0, the magnitude also goes to almost infinity. So this is the mathematical model that we have, and we represent it graphically like this. Okay. So we represent it with an arrow, okay, and that next to the arrow, we put a number which says the area under this Dirac delta function is 1. Okay, so we can have Dirac delta functions which have different areas. We'll see that in examples. Okay, so keep that in mind. So Dirac delta function basically is nothing but modeling spikes in change of signals. Okay, so whenever there is a derivative of a step function, or whenever there is a derivative of a function which changes instantaneously, then you are trying to model the spike or the change of slope of that. So there is a spike in the derivative, and that is modeled using Dirac delta functions. So the properties of Dirac delta function is that it is 0 everywhere except at one point, okay, and the area is always 1. The area is finite. That's important to note. Okay, what are the other properties? The Dirac delta function is an even signal. What does that mean? So del of t is equal to del of minus t. Okay, this is also pretty straightforward, because the way that we got to the Dirac delta function is through this rectangular function. The rectangular function is an even signal, which means that this has to be an even signal. What happens when you scale in time? Remember, once again, go back to how we got the rectangular function. We got through this. The scaling in time affects the Dirac delta function. Why is this? Once again, go back to the representation using the rectangular function. The rectangular function has width epsilon and height 1 by epsilon. So what happens to the rectangular function when you scale with time? obviously the function gets either compressed or stretched, which means the length gets scaled according to the time, but the amplitude still remains the same, which means this total area is now changing. The total area is now epsilon by A times 1 by epsilon, which is 1 by A, right? So the total area now gets scaled, and hence when you scale in time, even though the time duration for which the delta function is non-zero is almost equal to 0, it is infinitesimally small, the area changes. Okay, that you have to keep in mind. So even though you scale in time, let's say now I want to plot delta of 100t, right? In a graph, it still looks like this. Okay, it still looks like this. Okay, but now the area becomes much smaller. The time duration for which it is non-zero is still infinitesimally small, but the area now changes. So that is what you have to keep in mind. This is a very interesting signal where when you scale the signal in time, the area of the signal changes, but the length of the signal, the length in time of the signal still remains the same. This is very weird compared to other signals. So Dirac delta function is very special. So the Dirac delta signal has very interesting properties, and when you work with them, you have to keep in mind these properties. You cannot use them like other signals earlier. Okay, now what if we try to take the derivative of the step function which is time reversed? This is u of minus t. Remember, Dirac delta is an even signal, right? So clearly the derivative of this cannot be del of minus t, which is the same as del of t, right? So then what is this derivative? So as you can see here, earlier we obtained this the Dirac delta function as the derivative of step function, where the step increased from 0 to t, which means the slope was positive. Remember, how did we compute the slope? We said that it increased in a smooth manner like this, and the slope in this portion is positive. Whereas if the signal was decreasing from 1 to 0, basically you, let's say, open the switch. So the switch was always closed, let's say, then the voltage is always applied, and suddenly at one point you open the switch, then the voltage becomes 0. And what happens? The reverse of this happens, which is the slope was 0, so the signal's value is 1, and then it starts decreasing to 0. So this is what happens when you open the switch. So now in this interval, what is the slope? So if you compute the slope in this interval, then you get a negative value. Remember, this is a line which has an angle greater than 90 degrees. So the slope turns out to be like this. So this is epsilon, and this is 1 by minus 1 by epsilon. Okay. So what is the limit of this case? Basically, the limit of this case is when you tend epsilon to 0. So in this case, the Dirac delta function looks like okay. So the area is minus 1 now, because in the opposite direction. So we'll say that the derivative of a function which is falling or reducing instantaneously is given by the negative Dirac delta function. If it is increasing instantaneously, it is given by the positive delta function. If it is reducing instantaneously, it is given by the negative, that is minus of del of t. Okay. Now what if we multiply with a particular signal? Okay. So adding is easier. You just get one extra impulse at a particular point. Okay, this is what we call as the impulse. A spike at a point is what we say is the impulse, and that is also modeled by the Dirac delta function. And at what point does it exist? At t is equal to 0. So basically this point is t is equal to 0, and this point is t is equal to 0. We can do time shifting and time scaling. What is time shifting? t of some t minus t naught, which moves the signal to the right side. This is t naught. Okay. Time scaling we already saw. Now what if we multiply this with another signal x of t? Okay. So the property of the Dirac delta function is that if you are multiplying the function x of t with the Dirac delta function, the Dirac delta signal, then what happens is the area of the Dirac delta function gets simply scaled with the function's value or the signal's value at that particular time. Okay. So if this is x of 0, then when you multiply the Dirac delta function with x of t, the function is 0 everywhere except where the Dirac delta function is non-zero, because all other values are 0, 0 times any other value is 0. So here, what is the value of the Dirac delta function? It is now x of 0 is the area. Why is that? That is simply because the same case, right? So you have something like this. Now to this you are multiplying some other signal which has magnitude x naught. So the total area now will be of the form epsilon times x naught to 1 by epsilon. So if you compute the area, it is x naught, right? So this is the reason why we have the resultant of product of x of t with the Dirac delta signal to be just the Dirac delta function itself with the scaled area. Now what if you shift it? Of course, it's the same case, right? So it's the same case that you observe here. So it just gets multiplied with this point, which is x of t naught, right? So which would result in Dirac delta function at this point, which is x of, which has an area x of t naught. The location is t naught. Okay, so this is called the shifting property. Basically, you can just get out only one value of the signal x of t by multiplying that with the Dirac delta function. So if you want to find out the value of the signal at a particular time instant, then all you have to do is multiply with the Dirac delta function. This is as good as just taking a spike of the signal at a particular point. Okay, so this is a mathematical expression. So in reality, you cannot just generate Dirac delta functions wherever you want. The way that you have to do is you have to generate a lot of spikes. Okay, so if you are generating spikes and then multiplying with a signal, then what you are doing is essentially creating a spike of that magnitude at a particular point. Now clearly when you multiply the signal, the area gets scaled, and that's what we have. So you compute the area of the signal multiplied with the Dirac delta function, you get the area at x naught. So similarly, if you multiply the Dirac delta function t minus some t naught with x of t, then this area has to be x of t naught.